Hello, good evening, everyone, and I welcome you all to another session of these tutorial classes of thermodynamics session. And today is week 9, so and we'll wait for 1 or 2 minutes, and after that, I will be starting the class. So let me share my screen. Yeah, yeah. Okay, so in the previous classes, we have dealt sums of the cycles, that's the steam power cycle, and we have finished almost all the questions. So today, in the initial starting time, I will be doing questions related to gas power cycles, which were left due to the time constraint in the last class, and then I will be doing the sums that is related to properties of gaseous mixture. Okay. So, the first question is helium gas is used as a working fluid in an ideal Brayton cycle. The gas enters the compressor at 27 degrees Celsius, 20 bar pressure. The gas is heated to 1000 degrees Celsius, 60 bar pressure before entering the turbine. The cooler returns the hot turbine exhaust to the temperature of the compressor inlet. You have to calculate the work done for 2 kg of helium. Also calculate the efficiency of the cycle. You can take the Cp of the helium as 5.1926 kilojoule per kg Kelvin and gamma as 1.66. Okay, so before going to solve this question, first of all, let us see how the schematic diagram of a Brayton cycle looks. Okay, so just like the Rankine cycle, the Brayton cycle also has a combustion chamber. Okay, this combustion chamber was called boiler in your Rankine cycle, and here it is called combustion chamber. Okay, combustion chamber. Now where we will be putting some amount of heat Q1, okay, in order to heat up the fuel. So the fuel that will be entering, it will be a heated fuel that will coming out. So that is mostly coming out, and then after that it goes through a turbine. Okay, now this is a difference between the steam turbine and this turbine is that this does not deal any short of moisture content. So this is a purely gaseous turbine. So this is a turbine, so there will be some production of work which is called WT. Okay, after that it then comes through a cooler. Okay, in the other case we called it a condenser. The same work is done by another heat exchanger which is called cooler. Okay, so basically it will pass from this cooler. So as it is passing from this cooler, it will be releasing some amount of heat Q2. Okay, and then what will happen, in order to since this expansion takes place, and so in expanding the pressure drops, so you have to bring back to this original pressure level. For that you have to compress it. Okay, so for that a compressor is placed there. Okay, so that is the compressor, and that is termed as C, and which will require some amount of work WC. So this is the for a schematic diagram for a what you call Brayton cycle. Now why it is called ideal Brayton cycle, when we will solve this we will understand what is the difference between ideal Brayton cycle and a non-ideal Brayton cycle. So this is basically the schematic diagram. Now whether it is ideal or not, it depends upon this turbine, and we'll come to see. So then now if we name these processes, from here it is 1, it is 2, and this is 3, and it is 4, and then it is 4 to 1. So there are basically 4 processes, 1 to 2. Okay, so this process is isentropic, isentropic compression. Isentropic compression. Since it is isentropic compression, we already know that means this is reversible adiabatic. Okay, I will not write it because I have repeated it many times. Okay, then 2 to 3 is basically your isobaric heat addition. Okay, so that means constant pressure heat addition is taking place. Then 3 to 4 it is isentropic expansion, because it is turbine expansion work is taking place, so there will be reduction of pressure, so this is isentropic expansion. And from 4 to 1 this is basically your isobaric cooling. Okay, so there are 4 processes. Now the third step is what? We have to draw the TS diagram. TS diagram. Okay, now since no change in phase takes place, so there will be no any dome shaped in between, just like in case of Rankine cycle. So just the processes we need to show. So since the 1 to 2 step is an isentropic compression, and in compression temperature increases and isentropic, so entropy remains the same, so 1 to 2 will be this like this is basically 1 and this is basically 2. Okay, then constant pressure heat addition, so this is basically a P equal to C, so this is from 2 to 3. After that there is isentropic expansion, that means there will be reduction of temperature at constant entropy, this is 3 to 4, and then following the same slope as that of 2 to 3, this is your entire process. Okay, fine. Now in the question what it is given to us. Okay, fine. Now what it is given? It is given that the gas enters the compressor at 27 degrees Celsius. So before entering the compressor it is state 1, so that means T1 is given to us as 20 degree Celsius, which if we express in terms of Kelvin, this will be basically your 293 Kelvin. Okay, then your P1 is given as 20 bar. Okay, then the gas is heated to 1000 degrees Celsius and 60 bar pressure before entering the turbine. So before entering the turbine it is the state 3. Remember, before entering the turbine it is the state 3, that means your T3 is given. T3 is given as 1000 degrees Celsius, which in Kelvin it will be 1273 Kelvin, and P3 is given, that is 60 bar. Now we know that P3 is equals to P2 because this is a constant pressure addition, so this is basically equal to P2. Okay, and we also know that P1 and P4 will be same, so this is also basically P4. Okay, so now the cooler enters the hot turbine before exits, that's the same thing. The cooler exhausts to the temperature of the compressor inlet. Okay, so then you have to calculate the work done. So what will be the basically the work done? Work done by work done for 2 kg of turbine, that is basically your net work done you need to calculate. Net work done will be basically your WT minus WC. Now we already know how to calculate WT. WT will be nothing but H3 minus H4, and WC will be nothing but H2 minus H1. Now in earlier cases we have to calculate these enthalpies from steam table, because the operating what you call the fuel, or what you call the cycle on which it is running, the working fluid was basically steam. So that's why we had to look at the steam table. But here we should not look at the steam table, we have to look at the table of helium. But helium's table are not given. But one thing we know, that if it is not mentioned anywhere, this is basically an ideal gas. And for an ideal gas, enthalpy is equals to Cp into T. Okay. Okay. So for an ideal gas, your enthalpy is basically your Cp into T, ideal gas, and Cp is given to us as 5.1926 kilojoule per kg Kelvin. Also the gamma, that is the specific ratio Cp by Cv, is given to us as 1.66, which we will be using. Okay, these are the various things we are using. So in order to calculate the enthalpies, we need the different temperatures. We know T1, we know T3. So our motive will be to calculate T4 and T2. Fine. So our motive will be to calculate T4 and T2. Okay. So the process 1 to 2 is a reversible adiabatic process. So for a reversible adiabatic process, for process 1 to 2, what we can write? We can write T2 by T1 is equal to P2 by P1 to the power gamma minus 1 by gamma. Okay, we know T1, we know P2, we know P1, and from there I can calculate T2. That is basically T1 times P2 by P1 to the power gamma minus 1 by gamma. Okay, so just put the values. T1 value is, oh, this was 27 degrees Celsius, sorry. So this is basically 300 Kelvin. Okay, so that will be 300 into P2 is your 60, P1 is your 20. Okay, and gamma minus 1 is 0.66 by gamma is your 1.66. Okay, so your answer is 464.32 Kelvin. Okay, now similarly for process 3 to 4, okay, for process 3 to 4, what we can write? T3 by T4 is equal to P3 by P4 to the power gamma minus 1 by gamma. Okay, so from here we know T3, so we can calculate T4 is nothing but T3 by P3 by P4 to the power gamma minus 1 by gamma. Okay, now T3 we know it as 1273 Kelvin, 1273, and this is your 60 by 20 0.66, I 1.66. Fine. So from here we got T4 as 822.48 Kelvin. Okay, so now you have T1, you have T2, you have T3, you have T4. So what you can do? You can calculate WT, which is nothing but H3 minus H4. Okay, that is Cp times T3 minus T4. Okay, so what is your Cp? 5.1926. 5.1926. T3 is 1273 and T4 is 822.48. So this will be in kilojoule per kg. Okay, so this is your 2339.37 kilojoule per kg. Okay, similarly WC will be H2 minus H1, that is Cp times T2 minus T1, that is 5.1926 times T2 is 464.32 and T1 is 300. This will be kilojoule per kg. Okay, 5.1926, 464.32 minus 300. So this is your 853.248 kilojoule per kg. Now therefore W net is WT minus WC. Okay, what is WT minus WC? Basically that one minus this one, so it will be 2339.37 minus 853.248. so it is basically 1486.122 kilojoule per kg. Now this is the W net required for 1 kg. Now you have to require the work done for 2 kg. Therefore required work is 1486.122 into 2 kilojoule. Okay, that is your 2972.244 kilojoule. Okay, is it clear, the first part? Now in the second part we just have to calculate the efficiency. Okay, and we already know that efficiency eta is equals to output by input. Okay, and what is output? Output is nothing but W net, and input is what? Q1. Okay, we have already calculated W net, so W net was, we will do for per kg, so it is 1486.122 1486.122, and Q1 will be basically Cp times H3 minus H2. Cp times T3 minus T2. Okay, so this will be 1486.122 divided by Cp was 5.1926. 5.1926. T3 was 1273 and T2 was 464.32. 464.32. Okay. So the efficiency is 0.3539, that is 35.39%. Okay, so this was a very simple question. Now this was an ideal Brayton cycle. Now we will do a question which is non-ideal Brayton cycle. Okay, so in a gas turbine working on Brayton cycle, hot combustion gases from the combustion chamber enters into the gas turbine at 1450 Kelvin and 20 bar. Okay, and exits at 1 bar. The isentropic efficiency of the gas turbine is 0.90. Calculate the work developed by the turbine per kg flow of the gas. Cp value is given and Cv value is given. Okay, so the schematic diagram we already know, so I am directly going to the TS diagram once again. Okay, so there was a reversible adiabatic process 1 to 2 compression, then there was a heat addition. Okay, then there was expansion, then there was the heat rejection, that is cooling. Fine. Okay, now in a gas turbine working on the Brayton cycle, combustion gases from the combustion chamber enters into the gas turbine at 1450 Kelvin. Okay, that means turbine entering gases are given. That means T3 is 1450 Kelvin and your P3, which is nothing but P2, is equal to your 20 bar. Okay, these things are given to us, and exits at 1 bar. That means P4, which is also equal to my P1, is equal to 1 bar. Fine. Now the isentropic efficiency of the gas turbine is given. Eta isentropic is given to us for the turbine. Okay, this can also be given to compressor. So eta isentropic for the turbine is given to us as 0.90. Okay, now we have to calculate the work developed by the turbine per kg flow of the gas. Fine. Since the isentropic efficiency is given, that means what? That it is not going a reversible adiabatic process directly. Okay, so basically the turbine is going through this process. Okay, the turbine is going through this process, and let me name this as 4s. That means if it would have gone a isentropic process, it would have reached the point 4s, but it is not going in a reversible process, it is going in a non-reversible process. Okay, so that's why basically my process is this one. So it is reaching this point 4. Okay, fine, clear. In the earlier case it was directly going this way, but now some efficiency is given. That means it is not 100% isentropic, it is 0.90%. So it is 90% isentropic, so that's why it is having some bend. Okay, that means the entropy, whatever decrease should have happened, it is not having the total amount of entropy decrease. Okay, understood. Now from here we can calculate what? We can calculate T4s. Okay, So 3 to 4 3 to 4 process is not isentropic. So that's why we cannot apply T4 by T3. Therefore T3 by T4 is equals to P3 by P4 to the power gamma minus 1 divided by gamma is wrong. You cannot apply this. Very, very important, since this is not isentropic. But 3 to 4s is isentropic. So from here what I can do is that T3 by T4s is equal to P3 by P4 to the power gamma minus 1 divided by gamma. So from here I can calculate T4s is nothing but T3 divided by P3 by P4 to the power gamma minus 1 by gamma. Okay, so what is T3? 1450. What is P3? 20 by 1. Now what is gamma? Cp by Cv. Gamma is nothing but Cp by Cv. Okay, and Cp by Cv 1 divided by 0.769, it's 1.3. okay, so this will be 0.3 by 1.3. okay, so this is your 726.32 Kelvin. Fine. So we have got T4s. Okay. Now eta isentropic for turbine is what? H3 minus H4 divided by H3 minus H4s. Have you understood now? That means if out of this total entropy conversion from 3 to 4s, only 90% has been converted. Okay, so from here we can calculate H4 also, but we should not calculate H4, we should only calculate H3 minus H4, because we are required to calculate the work developed by the turbine. Okay, because we are required to calculate the work developed by the turbine. Okay, so from here we can calculate H3 minus H4 is nothing but eta isentropic of the turbine times H3 minus H4s. Okay, now this one I can write as Cp times T3 minus T4s. Okay, so from here eta isentropic is given to us as 0.90. Okay, Cp is given to us as 1, and T3 1450, and T4s is 726.32. Okay, this will be 651.312 kilojoule per kg, which is nothing but the work developed by turbine. Fine. Okay, now let us move to the next question. An engine operating on Otto cycle has a compression ratio 8:1. At the beginning of the compression stroke, the air is at 103.5 kilopascal and 300 Kelvin, and if the heat supplied is 920 kilojoule per kg, calculate the maximum pressure, the maximum temperature, and the cycle efficiency. CV value is given, and gamma, that is Cp by Cv value, is given as 1.4. Okay, now the ideal schematic diagram remains the same, only what will be changing is the heat addition processes here. Okay, in an Otto cycle, what happens basically? So processes of an, let me write here, of an Otto cycle. Okay, there will be an isentropic compression, then there will be a constant volume heat addition, then there will be isentropic expansion, and then there will be constant volume heat rejection. Okay, so that means it is different from Brayton cycle in these two processes. In Brayton cycle, these two were constant pressure heat addition and constant pressure heat rejection. Now in Otto cycle, it is basically constant volume heat addition and constant volume heat rejection. Okay, so let us draw the TS diagram first. Okay, so 1 to 2 compression. Now 2 to 3 is constant volume, 3 to 4 is expansion, and this is once again constant volume. Okay, so these two looks the same, only the difference will be in the slope, which we will be understanding in detail when we will be dealing with the diesel cycle. Okay, because in diesel cycle, one of the processes is constant volume heat addition, and the other process is the constant pressure heat addition is there, and constant volume heat rejection is there. So in that case, you will be understanding the difference between these two slopes. Okay, in case of TS diagram. Now let us also see how the PV diagram looks. Okay, now 1 to 2 is compression. So in compression, pressure will increase and volume will decrease. So basically this will look this way. Okay, pressure increased and volume decreased. Okay, then next is your constant volume heat addition. So V equals to constant, it will be basically a vertical line. Okay, so this is my 2 to 3. Now once again, this is also an adiabatic process, so the slopes of these two curves will also be the same. Okay, and then finally this one. So this is the simple diagram for PV diagram for your Otto cycle. Fine. Now what are the things that are given to us? It is given to us the compression ratio. Always the compression ratio is given. First of all, I will go with the what you call traditional way of calculating enthalpies at each point and then calculating the cycle efficiency, and then I will also derive an alternate way in which just by knowing the compression ratio you can calculate the efficiency of the cycle. Okay, now here we have to also calculate the maximum pressure and maximum temperature, so we are bound to go by the traditional way of calculating enthalpies at each and every point. Okay, so what are the things that are given to us? It is given to us the compression ratio. Okay, so given compression ratio. Now what do you mean by compression ratio? Compression ratio is nothing but volume before compression divided by volume after compression. Volume after compression. Okay, so what is the volume before compression? Volume before compression is V1 and volume after compression is V2. Okay, and this compression ratio, it is denoted as R suffix K. Okay, compression ratio. Now in case of Otto cycle, this compression ratio is also equal to V4 by V3. Is it clear or not? Because since V1 is equals to V4 and V2 is equals to V3. Okay, because of this only we can write this one, but actually the compression ratio is this one. You have to remember this: the volume before compression and the volume after compression, ratio of the volume after compression. Okay, so in Otto cycle, the compression ratio and the expansion ratio is basically equal. Okay, so to us the RK is given as V1 by V2, which is also equals to V4 by V3, is given to us as 8 compression ratio. Okay, then what it is given, that at the beginning of the compression stroke the air is at this one, so that means beginning of the compression stroke is means 0.1. Okay, so your pressure P1 is given as 103.5 kilopascal. Okay, and your temperature is given as 300 Kelvin. Okay, now the heat supplied is given. What is the, okay, so heat addition takes place at this process and heat rejection takes place at this process. Okay, so there will be this work of compression and there will be this work of expansion. Okay, so heat addition, that is Q1 is given as 920 kilojoule per kg. Okay, so and what are the things given? CV is given as 0.718 kilojoule per kg Kelvin, and the specific heat ratio, that is Cp by Cv gamma, is given as 1.4. Okay, now you have to calculate T max. What is T max from this diagram? What is the highest temperature in these 4 points? You have to look at the TS diagram and you see the highest temperature is 3. So we have to calculate T3. Fine. And also you have to calculate the maximum pressure. What is the maximum pressure from this diagram? So pressure diagram is P and V diagram. So the maximum pressure is also your 3 point. That's why drawing both the PV and TS diagram is important. So you have to keep in mind, you have to calculate P3, you have to calculate T3, and also you have to calculate the cycle efficiency, which we will be showing 2 ways. Fine. Okay, now we know T1. So in order to calculate T3, we should know T2. Why? Q1 is nothing but H3 minus H2. H3 minus H2. Now since this is an ideal gas, so this will be converted to, and its constant volume, heat addition is taking place in there, so it will be CV T3 minus T2, is not it? So heat addition at constant volume is nothing but CV T3 minus T2. Okay, now, and this Q1 value is given to us, so we know only T1. So if we know T2, then T3 is known to us because CV is given to us. Now how we will know T2 given T1? Okay, so for the process, for the process 1 to 2, okay, T2 by T1 is equal to P2 by P1 to the power gamma minus 1 by gamma, but we don't know the pressure ratios, but we know the volume ratio V1 by V2 to the power gamma minus 1, if you remember this relationship. Okay, this is for a reversible adiabatic process. Okay, now we don't know the pressure ratios, but we know the volume ratio, which is 8. So from here we can calculate T2 is nothing but T1 times RK, which I have denoted as RK to the power gamma minus 1. What is my T1? 300. RK is 8 and gamma minus 1 is 0.4. Okay, so it is 689.22 Kelvin. Let me write it nicely. 689.22 Kelvin. Now we will just put it here. Okay, so Q1 is given to us as 920 kilojoule per kg. Okay, CV is known to us as 0.718 kilojoule per kg Kelvin. Now we don't know T3, but now we know T2, and from here we can calculate T3, which is nothing but T max. Okay, so that is 1970.55 Kelvin. Fine, so this is your T3, which is nothing but your T max. Okay, now how will you calculate P3? Okay, so in order to calculate P3, once again we have to know P2. So from here we can calculate P2, because now we know T2, we know T1, we know P1, we know P1. Okay, so we will just put it here and then we will calculate P2. Okay, so we know that P2 by P1 is equal to V1 by V2 to the power gamma. Yes or no? Because for an adiabatic process, PV to the power gamma is equals to constant. So P1 V1 to the power gamma is equals to P2 V2 to the power gamma, and from that we know. Now V1 by V2 we already know. So from here we can calculate P2 is nothing but P1. What is P1? 103.5 times V1 by V2 is nothing but Rk, that is 8 to the power 1.4. Okay, so that will give you your 1902.24 kilopascal. Okay, so this is my Pmax, no sorry, this is P2 and this is my Tmax. Now how to calculate P3? So for the process 2 to 3, we can write P2 V2 by T2 is equal to P3 V3 by T3. Now 2 to 3 process is a constant volume process, so V2 and V3 will cancel each other, and from here I can calculate P3 as T3 by T2 times P2. Okay, so T3 I already know as 1970.55. Okay, T2 I know as 689.22 and P2 I know as 1902.24. Okay, so that is your 5438.697 kilopascal. Fine, so this is your Pmax. Okay, I have got Tmax, I have got this one. Okay, now I know T1, I know T2, I know T3. Now I can also calculate T4. Okay, so T3 by T4 will be nothing but V4 by V3 to the power gamma minus 1. Yes or no? Now what is V4 by V3? This is nothing but V1 by V2. Okay, so from here I can calculate T4 is nothing but T3 divided by Rk to the power gamma minus 1. Okay, so what is T3? T3 is 1970.55 divided by 8 to the power 0.4. Okay, so that will be your 857.73 Kelvin. Okay, now eta is what? Output divided by input, that is nothing but W net divided by Q1, which is nothing but Q1 minus Q2 divided by Q1, which is also nothing but 1 minus Q2 divided by Q1. Now what is Q2? Q2 is basically the heat released in the process from 4 to 1, and which is also a constant volume process, so that is also 1 minus CV times T4 minus T1. Okay, and Q1 we already know what it is given to us, but we can also write in this way as CV T3 minus T2. Okay, now this CV will get cancelled and we will just put the temperature values. Fine, 857.73 minus 300. T3 is 1970.55 minus T3 minus T2 is 689.22. 689.22. Okay. So that will be basically a 0.56. Okay. Now we can also do these things in alternate way. How we will do in alternate way? Just check it. Okay, I will derive the formula, which will just take a few minutes, and after that you will be able to do just by knowing the compression ratio. Okay, so alternately, for efficiency, okay, alternate formula for Otto cycle efficiency. Fine. So eta, we know that 1 minus q2 by q1, which we got, and that is nothing but 1 minus what you got. It is at T4 minus T1, and you got it as T3 minus T2. Okay, so what we know, T2 by T1 is equal to V1 by V2 to the power gamma minus 1. That means T2 is Rk to the power gamma minus 1 times T1. Okay, and we also know that T we also know T3 divided by T4 is equal to V4 by V3 to the power gamma minus 1. Here we have already done this thing. Yes, here T3 by T4 is equal to V4 by V3 to the power gamma minus 1. Okay, so from here we can write T3, because V4 by V3 is nothing but V1 by V2. We have already written it. You can go to the slide and you can check. This will be nothing but Rk to the power gamma minus 1 times T4. Okay, so we know these steps. Now from this we will put it just, okay, in place of this we will put it as T3 is nothing but T4 into Rk to the power gamma minus 1. Okay, and what is T2? T2 is nothing but T1 into Rk to the power gamma minus 1. Okay, now numerator we will put as it is. We will not put any change. From denominator, I think we can take Rk to the power gamma minus 1 as common. Okay, from here we will get this as T4 minus T1. Now this will get cancelled out. So what we will get as eta Otto is nothing but 1 minus 1 divided by Rk to the power gamma minus 1. If your compression ratio is given to you, you can directly calculate the Otto cycle efficiency. Now you can just put in the formula 1 minus 1 by what was Rk was nothing but 8, and this was 0.4. Okay, put all these values. Yes, you will get approximately that is equals to 0.56. Okay, so that means in either way you can calculate the efficiency for Otto cycle. Okay, now an ideal diesel engine has compression ratio 20 and uses air as the working fluid. Now the question is for diesel engine. Okay, and the state of the air at the beginning of compression is 95 kilopascal, and 20 degrees Celsius. Maximum temperature of the cycle is not to exceed this one. So that means your maximum temperature is given, so you have to determine the thermal efficiency. Cp and Cv values are given. Okay, fine. Now processes of diesel cycle. Okay, so what are the processes of diesel cycle? Number one, it goes through isentropic compression. Okay, then now the heat addition takes place at constant pressure. In case of Otto cycle, the heat addition takes place at constant volume. Okay, constant pressure, heat addition. Okay, the rest two processes are same, that is isentropic expansion and constant volume heat rejection. Heat rejection. Okay, now the TS diagram will be interesting because these are the same, only this thing is different. So let us first draw the PV diagram, then we will draw the TS diagram. Okay, so 1 to 2 is compression, fine, pressure increases and volume decreases. The second is constant pressure heat addition. So this is your heat addition. Okay, after that expansion, and then constant volume, okay. So 1 to 2, 2 to 3, 3 to 4, and then 4 to 1. Okay, now let us do the TS diagram. Okay, so this process will be 1 to 2, isn't it? Now this is my P equal to C. Okay, this will be the same straight line, vertical line. Now okay, let me draw this more clearly, then it will be perfect for you. Yes, yes. Now which slope will be greater? Will the P equal to C slope will be greater, or V equal to C slope? Because this process will be a V equal to C. So for that let us check. Okay, so we know Q is equals to TDS. Okay, and also we know Q is equals to CDT, whether it is CPDT or CVDT. It depends on whether it is constant volume process or constant pressure process. Okay, so from these two equations, what we can write as dt by ds will be equal to T by C. Okay, so for the same temperature process, okay, dt by ds, what is dt by ds? This is nothing but the slope of TS diagram. Okay, so dt by ds for constant pressure will be less than dt by ds of constant volume. Why? Because we know Cp is always greater than Cv. Now since Cp is greater than Cv, so for dt by ds for constant pressure will be T by Cp, and dt by ds for constant volume will be T by Cv. Okay, now since Cp is greater, so that's why this slope of this constant pressure will be less. So that means this will be much more steeper. Okay. So that will be the point 4. Clear? So this is V equal to C. Okay, fine. Okay, now let us see what are the things that are given to us. Okay, so an ideal diesel compression ratio is given to us, given, and we have already explained what is compression ratio. It's volume before compression and volume after compression, that is V1 divided by V2. That is your RK is given as 20. Okay, then state of the air beginning of the compression stroke, that means 1, at the state 1 it is given. So P1 given as 95 kilopascal. Okay, and your T1 is given as 20 degree Celsius, which we can write as 293 Kelvin. Okay, then maximum temperature, what is the maximum temperature in this? That is T3. Okay, so maximum temperature should not exceed 2200 Kelvin. That means my maximum temperature is T3, that is T max, it is nothing but 2200 Kelvin. Okay, now we have to determine the thermal efficiency of the cycle. So in order to determine the thermal efficiency of the cycle, you have to know the temperature at each and every points. So you know T1 and you know T3, and from those you have to calculate T2 and T1. Okay, sorry, T2 and T4. Now calculating T2 is very easy, because we already know 1 to 2 is an reversible adiabatic process. So T2 by T1 will be nothing but V1 by V2 to the power gamma minus 1. Now how to calculate gamma? Cp, let me check what is given. Yeah, Cp is 1.005 and Cv is 0.718. Okay, so gamma will be nothing but Cp divided by Cv, and if you do this, you will get this 1.4. Okay, so from here T2 will be nothing but 293 times 20 to the power 0.4. Okay, so that will be your 971.13 Kelvin. Okay, you got T2, you got T3, you got T1. Now you have to calculate T4. Now in order to calculate T4, we know the processes 3 to 4. Okay, so T3 by T4 will be equal to V4 by V3 to the power gamma minus 1. Now in the Otto cycle, this was nothing but equal to V1 by V2, but here this is not equal to V1 by V2 because these volumes are now different. Okay, so how will we do? That is the main thing. Okay, now in order to calculate V3, you should know V2. P2 V2 divided by T2 is equals to P3 V3 divided by T3. Okay, now these two are constant pressure processes. This 2 to 3 is a constant pressure process. So from here V3 is nothing but T3 by T2 to the power into V2. Now how you will know V2? Okay, so V1 by V2 is equal to 20. Okay, so from here V2 is nothing but V1 divided by 20. Okay, then how to calculate V1? P1 V1 is equals to RT1. From here V1 is equals to RT1 divided by P1. Okay, so again for an ideal gas, Cp minus Cv is equals to R. So R is 1.005 minus 0.718, which is nothing but 0.287. Okay, 0.287, and T1 is given to you as 293, and P1 is given to you as 95 kilopascal, and from here you will get V1. Okay, 0.287 times 293 divided by 95. Okay, so V1 is 0.885 meter cube. Okay, then now V2 will be equal to V1 divided by 20. Okay, zero point 0.4425 meter cube. Okay, and from here V3 is equal to, T3 is nothing but 2200, and T2 you got as 971.13. okay, into 0.04425. okay, and what is this? Basically 2200 by 971.13 into 0.04425. okay, so that is V3 is nothing but 0.1 meter cube. Now in order to know the this temperature T4, we also should know V4. And what is V4? It is nothing but V1, because this process is 1 to 4, 4 to 1 is nothing but a constant volume process. Okay, so we have already calculated V1, which is nothing but 0.885 meter cube. Okay, so from now from here we can calculate T4 is nothing but T3 divided by V4 by V3 to the power gamma minus 1. okay, so T3 was 2200. okay, V4 0.885, and V3 is 0.1 to the power 0.4. okay, 2200 divided by 0.885.1 to the power 0.4. okay, so that is 919.698 Kelvin. okay, now cycle efficiency is 1 minus Q2 by Q1 again. okay, but now interesting thing is that Q2, this is Q1 and this is Q2. so Q2 is a constant volume process, so that will be CV times T4 minus T1, and this will be CP times T3 minus T2. Okay, so that means what I can write this one is 1 minus T4 minus T1 gamma into T3 minus T2. Okay, T4 is 919.698, and T1 is 293. Okay, gamma is 1.4, T3 is 2200, and T2 is 971.13. Okay, so that is your 0.6357. Okay, now also there is one more alternate way to calculate the efficiency of a diesel cycle. Okay, and if time permits today I will do the derivation, but because I have also to do the questions related to your properties of gaseous mixture. Okay, you just write the formula. So eta diesel is 1 minus Rc to the power gamma minus 1 divided by gamma into Rk to the power gamma minus 1, okay, into Rc minus 1, where Rk is compression ratio that is V1 by V2, and Rc is your cutoff ratio. Which is nothing but V3 by V2. Okay, so this derivation I can do, but I will do the properties of gaseous mixture questions first, and then if the time is permitting, then I will do this one. Okay, now let us move to gaseous mixture sums. So a gaseous mixture contains equal number of hydrogen and nitrogen molecules. Specific heat measurements on this mixture are taken at temperature below 150 Kelvin. What is the value of gamma? Okay, so you have to calculate the value of gamma for the mixture. Okay, there is a mixture. Okay, and this mixture contains hydrogen plus nitrogen, and if there are n moles of hydrogen, okay, then there will be n moles of nitrogen. That means the mole number of these two are the same. Okay, now if they are saying nothing, then we can assume everything as ideal gas, and all these measures are taken at a temperature below 150 Kelvin. Okay, so we have to calculate the gamma for the mixture. Now for an ideal gas, the CV is equals to F into R divided by 2, where F is the degree of freedom. Okay, so for monoatomic gases, now monoatomic gases like helium and argon, F is equals to 3. Okay, this implies CV is equal to 3R by 2. Okay, and for diatomic gases, for diatomic or linear polyatomic so diatomic, linear polyatomic, like hydrogen, okay, nitrogen, oxygen, okay, the degree of freedom is 5. Okay, so therefore your CV is 5R by 2. Okay, and for non-linear polyatomic gases like ammonia, carbon dioxide, okay, the degree of freedom is 6. Okay, so their CV is basically 6R by 2. Okay, now in our case, uh, hydrogen and nitrogen are given, which are diatomic gases. Okay, so CV of hydrogen is nothing but 5R by 2. Okay, also the CV of nitrogen is 5R by 2. Therefore the CV of the mixture will be N1 CV1 plus N2 CV2 divided by N1 plus N2. So this is the formula for finding the mixture. So if there are n components, so basically you will weight by the number of moles that is present with the individual CV divided by your total number of moles. Okay, so here N1 is nothing but my number of moles of the hydrogen. Okay, so let me assume the number of moles of the hydrogen as N. So as per the question, the number of moles of hydrogen and nitrogen are the same. Okay, so from here we will get this as 5R by 2. Okay, now this is CV. Then the mixture of two ideal gases, they are non-interactive mostly if you are considering this as ideal gas, so it again remains the ideal gas. So for an ideal gas we know that Cp minus Cv is equals to R. Okay, so from here I can write as Cp of the mixture is nothing but Cv of the mixture plus R. Okay, so what is the Cv of the mixture? 5R by 2 plus R. So I think this will be 7R by 2. So therefore gamma of the mixture is nothing but Cp of the mixture divided by Cv of the mixture. Okay, so which is nothing but 7R by 2 divided by 5R by 2, so that will give you 7 by 5. Okay, fine. Next question. 1 mole of nitrogen at 1 bar was mixed with 2 mole of oxygen at 1 bar. Okay, and the final pressure is 1 bar. The gases are ideal and the mixing is isothermal. Okay, so find the total entropy change. Okay, what it is telling, that nitrogen and oxygen, they are mixed. and they are mixed to form a mixture of oxygen plus nitrogen. Okay, conditions were 1 bar, 1 bar, and the final mixture was also 1 bar. Okay, and 1 moles of nitrogen and 2 moles of oxygen. So what is the total number of moles here? 3 moles. Okay, so therefore mole fraction of uh, nitrogen, that is X N2, is equal to what? Number of moles divided by total number of moles. Similarly, mole fraction of oxygen, that is X O2, was 2 by 3, that is in the mixture. Okay, now we know that partial pressure Pi is equals to Xi into total pressure. Okay, so that means partial pressure for a particular element I in a mixture is nothing but mole fraction of that element into the total pressure. Okay, so what is the total pressure here? 1 bar. We know the mole fraction here, so therefore partial pressure for nitrogen is what? 1 by 3 into 1 bar, that is 1 by 3 bar. Similarly, partial pressure of oxygen is nothing but 2 by 3 bar. Okay, so that means from 1 bar nitrogen went to 1 by 3 bar, and from 1 bar oxygen went to 2 by 3 bar. And now in this process we have to calculate the entropy changes. Okay, so entropy change for an ideal gas is what? Cp ln T2 by T1 minus R ln P2 by P1, where 2 is the final and 1 is the initial state. Okay, now this is an isothermal process, so this step will be automatically equal to 0. Okay, now this is for 1 mole. For n number of moles, this was basically n into R. Okay, so that means delta S of N2 will be nothing but minus n N2 into R into ln P final by P initial. Okay, so number of moles was 1. R is the universal gas constant, and we know this one is as 8.314 times ln 1 by 3 by 1. Okay, so that is your 9.1338 joule per Kelvin. Okay, similarly delta SO2 will be nothing but minus NO2 times R times ln P final divided by P initial. Okay, so that is 2 into 8.314 into ln 2 by 3 by 1. Okay, so that is your 6.7420 joule per Kelvin. Okay, so therefore delta S mixture is delta S N2 plus delta S O2. Okay, so that will be 9.1338 plus 6.7420 15.8758 joule per Kelvin. Okay, fine. Next is consider a gas mixture that consists of 3 kg of oxygen, 5 kg of nitrogen, and 12 kg of methane. Determine the mass fraction of each component, mole fraction of each component, and average molar mass and gas constant of the mixture. Okay, so there is a mixture of oxygen plus nitrogen plus methane. Okay, and oxygen there is 3 kg. Okay, nitrogen there is 5 kg, and methane there is 12 kg. Okay, so total it is 20 kg. Okay, so number 1, we have to calculate the mass fraction. Mass fraction, that is MFI, is nothing but MI divided by M total. Okay, so therefore MF, mass fraction of oxygen, is nothing but mass of oxygen divided by M total. So that will be 3 by 20. Similarly, MF nitrogen, it will be mass of nitrogen divided by M total. That will be nothing but 5 by 20. And mass fraction of methane, that will be mass of the methane divided by M total. Okay, and mass of the methane is 12 by 20. Okay, now next step is mole fraction. Now mole fraction is denoted as X. So mole fraction for the ith one is equal to Ni by N total, where Ni is number of moles of ith component. Okay, now mole fraction formula is what? Given mass divided by molar mass. Fine. So therefore Number of moles of oxygen will be what? Given mass of oxygen divided by molar mass of oxygen. Okay, so given mass of oxygen is 3 kg and molar mass of oxygen is 32 kg per kilomole. Okay, so that will be 0.09375 kilomoles. Okay, similarly, number of moles of nitrogen, that will be given mass of nitrogen divided by molar mass of nitrogen. Given mass of nitrogen is 5 kg and molar mass of nitrogen is 28 kg per kilomole. Okay, so this is 0.1785 kilomoles. Similarly, number of moles of methane is given mass of methane divided by molar mass of methane. Given mass of methane is 12 kg and molar mass of methane is 16 kg per kilomole. Okay, zero point 0.75 kilomole. Okay, so now mole fraction, that means X of O2 is nothing but N of O2 divided by N of O2 plus N of N2 plus N of CH4. Okay, so this will be 0.09375 divided by 0.09375 plus 0.1785 plus 0.75. Okay, 0.09. Okay, similarly X of N2, that will be 0.1785 divided by 0.09375 plus 0.1785 plus 0.75. 0.1746. Okay, and CH4 mole fraction is 0.75 divided by 0.09375 plus 0.1785 plus 0.75, that is 0.09375 0.7336. Okay, fine. Now next question is this one done, this one done. So calculate the average molar mass and gas constant of the mixture. Okay, so average molar mass, will be m total divided by n total. Okay, so what is m total? It is 20 kg. And what is n total? It is this one plus this one plus this one. Okay, so that means 0.09375 plus 0.1785 plus 0.75 kilomole. So the answer will be kg per kilomole. Okay, 20.09375 plus 0.1785 plus 0.75. Okay, so that will be 19.56 kg per kilomole. Okay, then gas constant will be universal gas constant R star divided by molar mass, that is this average molar mass. Okay, so R star is nothing but 8.314 kilojoule per kilomole into Kelvin, and this is nothing but 19.56 kg per kilomole. Kilomole got cancelled out, so this will be 0.425 kilojoule per kg Kelvin. Okay, now air is a mixture of 78.1% nitrogen, 20.95% oxygen, and 0.9% argon, and 0.05% carbon dioxide. What is the mole fraction? So this is given in mostly by volume. By volume is given, so volume percentage is given to us. Now you have to calculate the mole fraction of nitrogen. Okay, so volume fraction Vf of the element I is nothing but volume occupied by the element I divided by total volume. Okay, so therefore given Vn2 divided by Vt is equal to 0.2095. Okay, similarly this is nitrogen is another sorry, yes, so that is 0.781 nitrogen. Okay, and V oxygen divided by total volume, it is given as 20.95%. It will be nothing but 0.2095. Okay, Then V argon divided by total volume is your 0.009. Okay, and V carbon dioxide divided by V total is 0.0005. Okay, these are the given to us. Now we know ideal gas equation PV is equals to N R star T. When number of moles is there, this is basically the universal gas constant. Okay, so therefore PV total will be equal to N total R star T, because whenever there is any mixture, the total temperature will be always equal to your individual gases temperature. Okay, and suppose there is we want to calculate for nitrogen, and this will be number of moles for nitrogen times R star into T. So now if we do 2 divided by 1, okay, so that will be volume of nitrogen divided by volume total. This will nothing be but N of nitrogen divided by N total. Now what is N of nitrogen divided by N total? This is basically your X of nitrogen, that means mole fraction of nitrogen. Okay, so mole fraction of nitrogen is equals to the volume fraction of nitrogen. Okay, and the volume fraction of nitrogen is 0.781. Okay, so from here we know that the mole fraction of any element is nothing but the volume fraction of that element. Okay, fine. Now in a Death Valley, temperature can reach up to 52.1 degrees Celsius with air pressure as high as 762.4 mm mercury. How many grams of oxygen are there in 1.89 liter of this air, assuming that the composition given in question number 8? So composition of oxygen remains the same as that was there in question number 8. Now if in that Death Valley the temperature drops to 52.1 degrees Celsius and the pressure is this much of mercury, and there is 1.89 liter. Now since liters are given, so we will write the universal gas constant R star in terms of liter atmosphere. Okay, so R star will be 0.0821 liter into atmosphere per mole per Kelvin. Okay, now given T 52.1 degrees Celsius. Okay, (325) Kelvin. P is 762.4 mm mercury, and you already know that the density of mercury is 13.6 into 10 to the power 3. So rho gh will apply 13.6 into 10 to the power 3 rho. G is 9.81 and h is your 762, that means meter 0.7624. okay, so that will be in Pascal. So this will be basically your 1.019 into 10 to the power 5 Pascal, which I can write as 1 atmosphere. because 1 atmosphere is also 1.013 into 10 to the power 5 Pascal, and the total volume in the air is given as 1.89 liter. Okay, now from question number 8, what we know, the volume fraction of oxygen is 0.2095. And what is volume fraction? That is basically volume of oxygen divided your total volume. So from here I can calculate what is the volume of oxygen present. Okay, 0.2095 into 1.89 liter. So this much volume of oxygen is present. Okay, 1.89 into 0.2095. So that is your 0.396 liter. Okay, so this much volume of oxygen is present. Now ideal gas equation, so if number of moles is there, we can write this one in universal gas. Okay, so we know T, we know P, we know V, we know R star, and from here I can calculate number of moles of oxygen that is present in this much volume. Okay, so what is the P here? 1 atmosphere, volume 1.89, fine, and no, sorry, volume is 0.396. That was the total volume. I'm very sorry. Zero point 396. This is my volume of the oxygen. R star is 0.082. Okay, and temperature is 325.1. Okay, zero point 0.01485. This much number of moles are there. Now we also know that number of moles is equals to given mass. I will write number of moles is equals to given mass divided by molar mass. Now we have to calculate the given mass of oxygen, so therefore mass of oxygen present is what? Number of moles of oxygen times molar mass of oxygen. Okay, so what is the number of moles of oxygen we got? 0.01485. And what is the molar mass of oxygen? It is 32 grams per mole, and here number of moles are there, so into mole, so mole and mole got cancelled. This much gram will be there. 0 0.4752 grams. Okay, so I have one more question left, but that is a bit lengthier question. Just like the today's class, I will do this question before starting the week 10 lecture, and I will wait for 10 more minutes in order to discuss like any doubts you if you have in today's class or the previous classes. Okay. Okay, we'll stop this class today and hope you understood. Okay, we'll continue in the next class. Thank you.